It's a great pleasure to have Shehryar here, who is going to tell us about the modular Hitchin system.
Thank you so much, and thank you for the invitation. It's really quite an honor to speak here, especially, I'm pretty sure it's preaching to the choir about the Hitchin system. And let's hope there's something interesting coming out of it by looking at it over a modular curve. So yeah, I think the talk just is given away just by the title. So to start off, so let X be a smooth projective geometrically irreducible curve over some field, well, some algebraically closed field. Okay, but for the most part, we will take K to be equal to C, and later on in the talk, we'll need to go to Q bar and stuff like that. So as of now, X is our good old compact, connected, smooth Riemann surface. And there's an age-old story that once you have X and you fix a complex reductive Lie group, you can associate space, well, certain spaces to this pair X and G, namely G bundles, well, G semi-stable bundles on X, and G semi-stable Higgs bundles on X. And the relation usually is that the cotangent bundle is contained and the Higgs bundle has a dense open set. And well, there's too much to be said about these spaces. They show up everywhere. And classically speaking, G equals C star was the first case where we just look at the Jacobian of the curve. But there's well, I learned this principle in mathematics from Don Zagier, that whenever you have something which depends on a parameter, try to fix it at a point with some special properties. So for example, when it depends on a curve X, we can look at special points in the moduli space of X. Special points being where X has some extra symmetries, and try to show how those symmetries manifest themselves either in these spaces, and use those symmetries to study these spaces. For example, the topology of these spaces. So one special kind of curve is the modular curve. So if we fix X to be a modular curve, so I'll define these in more detail later. They come in different flavors. So X to be a modular curve, let's say Xn, X1n, or X0n. Then something nice actually happens. So we do know that there is this map from G, and okay, and for simplicity, let's also fix G to be SL2C from now on. And this is not a big restriction, but it just simplifies things. So in this case, we have this map, and MH will denote moduli space of semi-stable Higgs bundles, semi-stable SL2C Higgs bundles. We have a map from MH, and for now I'm just taking Xn, but we'll actually, let me take X1n. I'll define this later. There's a map from here to H0 of K squared X1n. Well, this is the standard Hitchin map, which makes this, well, this is a symplectic manifold, and it makes it into an algebraic integrable system. But the special thing happens when you have X1n. So there's this morphism between weight 4 cusp forms on gamma 1n or xn. So there's these weight forecast forms associated with the modular curve, and this base of the Hitchin system. So this is more general actually. This is, if we take, instead of k squared, we take, let's say, the mth power. The isomorphism is between 2m and this thing. And it's a very simple isomorphism, so I'll recall this later. And so as soon as you have this, I mean, this is the first point where a red light goes up in your mind that there must be some special things that can happen in this situation because you have these weight forecast forms. So let me just give the very basic structure of this vector space and these cusp forms. And then we'll try to see how much of it we can actually translate or use in this Hitchin system business. So the main thing are Hecke operators. So there is a for all primes p such that they don't divide this level n that we've chosen. So actually I should also mention that we choose x1n. To choose x1n such that the genus is bigger than or equal to 2, so that we actually have an interesting moduli space to deal with.
Could you remind us quickly what is x1n, or what are the three of them?
Yeah, I will define all three of them in a bit. So this is just the introduction into this kind of thing. Yeah, so for all primes p which don't divide n, we have a linear operator. Tp from S4n in this case. And a basis F1 Fm such that each Fi is an eigenvector for all Tp. Again, P such that it doesn't divide n. So and such an eigenvector or a Hecke eigen form has an expansion. Every modular form has an expansion, but this is going to be a little special. With n bigger than or equal to 1, a and n, q to the n. So here q is e to the 2 pi I tau, and tau is, well, in h mod gamma 1 n. So this is our curve x1n. So this is the basic structure, the very first structure that you have on this vector space. And the question, so now there are some natural questions to ask for, and I just want to write them down before I get into detail of defining these curves and everything. So I guess the first question is, can one lift the action of Tp from the base to the entire moduli space MH. And by lift over here, I really mean the lift as correspondences. I'll explain what they are later. Number 2. So let F be an eigenvector for TPs. Is the arithmetic of SF. So SF is the spectral curve corresponding to this element in the base of the Hitchin system. related to these coefficients A and F. What is this thing? Related to specifically these coefficients. And in general, it would be very nice to somehow find an interpretation or reincarnation of these coefficients of modular forms in the geometry of our Hitchin system. Because that's really, there are very many conjectures related to these things and very many nice theorems related to these things as well. So it would be nice to see them in the geometry of this thing. And all of this, so if G was equal to C star and we're looking at the Jacobian, there's a very nice interpretation of the arithmetic and the arithmetic of these coefficients and the arithmetic of the Jacobian. So I'll just recall that quickly. That was all the Shimura's results. And the last thing is soon enough.
I'm just confused of what
Yeah.
you mean by the arithmetic of the cover. You mean that you want to look at it as defined over the number field with those numbers added to it, and
So yeah,
and
so
then look at rational points. I mean, what
Exactly.
does arithmetic mean?
okay, so first of all, the first question would be, given such an expansion, as of arithmetic, by that I mean the following things. What is the field of definition? So your curve x1n is defined over Q, and then SF is a double cover in this case over these things. So is the field of definition of SF a quadratic extension of Q, number one? And if it is, how is it related to the field of coefficients, to the field generated by these coefficients? So I'll get to that later. And then once you have a curve over an algebraic number field, say that it is defined over an algebraic number field, the first basic thing to ask is what is its Hasse-Weil zeta function, or just counting points over prime ideals of that field. So that's what I meant by the arithmetic. And third is soon enough we will realize that all these modular curves have these nice properties because they really are not just Riemann surfaces, but they are moduli spaces of elliptic curves with certain structure. All of them, x1, x0, and xn. And so let me just say that what we really have is a family of elliptic curves over x1n. So if we have a tau in here, the fiber is an elliptic curve E tau, and in the case of x1, it's a point of, so Q is a point on this abelian group of order n precisely. I'll make sense of this a little more. But the point is that x1n and these modular curves don't just come by themselves, but they come in a family, or they naturally parameterize a family of elliptic curves with extra structure. And the question is that, let me, maybe, so our Higgs bundles on x1n related related to some four-dimensional gauge theory on this family E. And if yes, what role does the spectral curve play in the 4D theory? So the reason I'm asking this, or stating it really as a question, is the following thing, that you'll see that the Hecke operators, the reason they act on this vector space is essentially because they act as correspondences on this four-dimensional manifold or this two-dimensional algebraic surface. And to really lift this action as correspondences on everything, we have to lift it to spectral curves of the fibers. And it would be somehow very nice if a given spectral curve SF embeds in this total family over this thing x1n. We do know that it embeds in the total space of a certain line bundle over this, but it would be nice to have it embedding in this in this family of elliptic curves, because the Hecke operator is naturally active. So these are the questions, the first questions that come to your mind as soon as you have that structure of a modular curve. And that's what I want to answer. So I have some kind of answer for this one and some kind of a vague answer for this one. And of course, there's probably not a unique way of lifting these as correspondences such that they cover everything. But I do want to get to that.
Can you say a little more about the last question?
About the last question?
So SF is a spectral curve that sits inside the cotangent bundle of Xn, and you want to know whether it also sits in another surface, which is the elliptic surface.
Exactly. Yes. So SF, so
what's the
F,
reason
maybe I
for
should
that?
write phi. So the thing is, you take an X bundle E phi on X1n. You have the spectral curve S phi. And the question, so we know that S phi embeds in the total space of the canonical line bundle over this thing. The question is that does it also embed in this elliptic surface?
So what makes you think that it should?
Well, conversations with you. I don't want to give it away right now. But so at some point you explained that Higgs bundles on this thing can be considered as vector bundles on the total thing. And the spectral curve of the Higgs bundle downstairs does embed in the elliptic surface. And I have to admit that I didn't go through that paper yet, but that's why I was saying this mostly. And the reason it would be nice, I mean, I can tell you why it would be nice to have such a thing, is because the Hecke operators really act on the entire thing. So then, once you have a spectral curve sitting in there, one can just look at the action of the Hecke operators restricted to this embedding. It might not be an embedding actually, it might be an immersion or something even more messed up. But so yeah, that's the reason why I'm basically looking for something like this. And in either case, because Hecke operators act on the entire surface, they would act on, I think they would act on any gauge theory that you have, any four-dimensional gauge theory that you might have on this elliptic surface.
This brings another question, which is, are you viewing the modular curves as curves, as orbifolds, as what?
Yeah, so we will have to, so modular curves are not only orbifolds but a little more messed up. So they have cusps. They will have elliptic fixed points, but they also have, I mean, you need to compactify them in a certain way, so I'll come to them. So we really need to view them as orbifolds. That's why I didn't write just 3g minus 3 over here. Because you have to use the orbifold Riemann-Roch, and that doesn't really give you 3g minus 3. It depends on how many elliptic points you have and what is the torsion data attached to them. Now, this problem can be avoided if instead of modular curves, you consider Shimura curves. So Shimura curves are more difficult to define, but they really are genuine compact Riemann surfaces without any orbifold points or cusps. And they have this action of Hecke operators on their holomorphic differential forms. The only thing is I don't want to introduce them in this talk because it would just take a lot of time just to introduce them. And then the actual thing that we are after would be missed, which is somehow the action of Hecke operators. Okay, so
No, the reason I ask is because if you are, if you are taking into account the orbifold structure of the modular curve, then if you look at the elliptic surface as a surface over the coarse moduli space of the orbifold curve,
yeah,
it has no reduced fibers.
yeah,
And that means that you have to introduce parabolic structures for those Higgs bundles there.
Right.
If you have any, you want to have any call
Right.
for the Higgs bundle to be interpretable in terms of gauge data on the elliptic surface.
Right. No, I absolutely agree that the right way to look at it is parabolic bundles with specific parabolic structure at the orbifocal points. Now there are modular curves where which are torsion free or which have no orbifocal points. So
That's just by
very
adjusting the
very
level
specific.
structure or what?
Sorry.
This happens if you adjust the level structure to be special? Or?
Yeah. There are some levels where you will have no orbifold structure. For example, gamma 2. Gamma 2 is basically P1 minus 3 points, and when you compactify it, you add 3. So there are certain subgroups of certain congruent subgroups of SL2Z which have no torsion.
Anything of high enough level.
Yes, even in high enough levels so that genus is bigger than or equal to 2. These things do exist, but very sparsely.
Oh, so it's not everything of high level.
No. There will be, there will be higher levels where there will be torsion and the group is not torsion. What I am more worried about are the cusps. So, let's do that. The elliptic points can be gotten rid of by making special choices of them. So since it's...
And these are cusps in the sense of number theory, which is different than cusps in the geometry.
It just means singular fibers in the elliptic surface.
Exactly.
Smooth points of the spiral cover, of which the fiber E is singular.
Yes, exactly. And not just singular, but very specific singular ones. So cuspidal ones are not allowed, only nodal.
Yeah, only nodal. Simple.
Simple nodal. So I guess, should I just skip the entire background on the Hitchin system? I guess this crowd that's like preaching to the choir.
I think that's safe here.
Yeah? Okay, let me just write the highlights, just the... This is, okay, let me just, write down the definition more specifically. So if X were right now not if X were just a smooth projective curve, then we define MHX, so this is going to be modular space of SL2 Higgs bundles E to X, so define it to be where E phi, where E to X is a holomorphic vector bundle, and phi is a map from E to E tensor kx. Rank of E is 2. Top exterior power of E is trivial, semi-stable, and what we're looking for are S equivalence classes. So let me just say S equivalence. This thing is a quasi-projective variety. Dimension equals 6G minus 6. And there's this map. Simply given by its determinant. And I guess the main property of this map is that will not get into this, but MH is a holomorphic symplectic manifold. So omega is not just a 2 form, but a holomorphic. So it's a 2-0 form on MH, and closed and non-degenerate, so making it into a symplectic manifold. And if we choose a basis for this thing, let's say we choose some basis F1 to F3G minus 3, and let's call this map H. Then the components of H, Fi, comma H, Fj, the Poisson commute with respect to the bracket given by the symplectic form. And this is in classical mechanics, in the good old Newtonian mechanics in the world of F equals ma. Arnold realized that once you have this structure, the fibers of H for a generic element in here are open sets in well, in real tori in general and in complex tori in this case. So let me just write it quickly. The H inverse of F generic is contained in C to the exactly of half dimension. So and the main, well, Hitchin's main realization, I guess, is also that there exists a spectral curve SF, which is 2-to-1 cover of the original curve X, branched at zeros of F, and smooth if and only if F has simple zeros. Actually, I should have just said that it's a complete integrable system, and I think that would have been enough. So that's the structure, and the fiber for F generic H inverse F is biholomorphic to the prim variety of the spectral cover SF. And the prim variety is defined as follows. So you have the Jacobian of SF, and it's equal to the Jacobian of your base curve times what is left as. So what is left is called the prim variety. And the way to look at it is that since it's a 2-to-1 cover, there's an involution here such that SF quotient out by that involution is equal to X. The involution also acts on line bundles or on Jacobians. Jx is the positive eigenspace, and the prim variety is the negative eigenspace or the invariant line bundles. In other words, these are the line bundles which are not pullbacks of line bundles from X. And one more property which I hope to use by the end is that MH is a hyperkähler manifold, and it's related to this. So there's this very nice diagram that the moduli space of Higgs bundles is at least as a set equivalent to what I call the solutions to Hitchin's equations, which are then equivalent to flat connections, flat SO2C connections on your curve X. And this, by an old theorem of Weyl, is equivalent to SO2C represent irreducible representations of the fundamental group of X. So this correspondence is called the non-abelian Hodge correspondence, and it finally gives a map between Higgs bundles and these representations. So the right way to look at it, at this thing, is that it's actually a smooth manifold with a hyperkähler structure, and MH is seen in one hyperkähler, but in the complex structure I, and this thing is seen in the complex structure J, and then the third one is of course the combination. So these are the two biggest things about this, and these are the structures that we will use. So now we come back to our spectral curves, to our modular curves. So we have this SL2R action on the upper half plane, which is a set of complex numbers such that imaginary part of tau is positive. And the uniformization theorem tells us that any hyperbolic Riemann surface is a quotient of H by a discrete subgroup of SL2R. So now that we have this group, there's one natural group which is a little more special, at least arithmetically, and that is, so we'll call that gamma 1, and that's equal to SL2Z. So the quotient of H by gamma 1 is called, usually defined to be Y1. So this looks like the following thing. We have the fundamental domain, 1, these things go to half, and minus half. So that's what the fundamental domain of SL2Z looks like. And the quotient, Y1, is a hyperbolic surface with one cusp, so one puncture coming from this point at infinity, I infinity, and two special points called, well, two special orbifold points, namely one coming from here, and the other one is this fixed point. So because this is fixed by the involution, it's of order 2. So let's say this is this one and this is this one. So that's what the curve looks like. And there's just like there's a standard way of compactifying C to the Riemann sphere P1 by adding one point at infinity. There's a way of compactifying the modular curve as well by adding what is called a cusp at I infinity. So once you do that, it becomes a finite area hyperbolic surface. So I will call, I will denote the cusps by X and the orbifold points by dots.
So again, is this considered as a coarse modular space or as an orbifold?
Coarse modular space. I mean, so the modular interpretation comes in now, and we'll consider it as both, but use the coarse modular space because it's easier to work with, at least in the start or in the beginning.
Because if you consider it as an orbifold, there is also Zemo 2 on top of it.
Yeah, over these points.
No, everywhere.
Over everywhere.
Because the center of SL2Z are restricted.
Ah, yeah, that's true. So the plus minus identity, right? Okay. So let's consider it as a coarse moduli space as of now. And this compactification, by adding a cusp to this thing, we will denote that by, and that's what we will really use, by x1. So the first thing, I mean, it does look a little special because we've restricted from SL2R to the ring of integers of this field, SL2Z. But the real special property of this curve comes from the following fact, that for any tau in H, we can associate a lattice lambda tau as Z plus tau Z to Z2. And of course, with this, we can construct a complex torus, complex one-dimensional torus E tau. And so two complex tori turn out to mean there's a natural isomorphism, there's a natural equivalence on the complex tori that there's a biholomorphic. So two complex tori are equivalent if there's a biholomorphic map between them, which is also a group morphism with respect to this thing. And after this equivalence, it turns out that this x1 is the moduli space of complex tori. Actually, it will turn out to be moduli space of elliptic curves soon enough. But as of now, it's the moduli space of complex tori. So over this thing are lying these rank 1 things. And all the nice properties really come from this family. And that's why I made that third question, because soon enough it will make sense that it's better not to look at Higgs bundles on the curve downstairs, but see how they're related to the entire family, or the 4-dimensional. So all the formulas that I will write down for modular forms and their expansions will be for this particular one because they're the easiest to write down on the blackboard. But so this is of course of genus 0, and one can build other examples of curves as well. So now I introduce these three things. There's gamma n, which is the set of matrices ABCD in gamma 1, such that they're congruent, such that they're the identity mod n. And over here, mod n really means entry. So for each entry, you consider it mod n. This naturally is a normal subgroup or in the kernel of gamma 1. So where we map gamma 1 to SL2 Z mod n Z. And to build more, so now we can take H mod gamma n and we get a curve which might be of higher genus, and it will have a different modular interpretation which I will come to in a bit. And likewise, one has other arithmetic groups, gamma 1n. Just for the ease of notation, I'll write that ABCD is congruent to 1, 1, 0. And this means it can be any integer. Is congruent to this mod n. And gamma 0n is the same thing, but all these three are allowed to be different. So this was the question that was asked first. Now, what is the modular interpretation here? We can already see that it has to be different because gamma 0 is the biggest group, which contains both of them. So I will just state what it is. So gamma 0n is the moduli space of equivalence classes of following things. It's a so elliptic curve E tau and a point of order n c. So equivalence classes of this thing. So C is really a subgroup of E tau of order n, because we're considering. So this will be the modular interpretation for gamma 0n. In other words, C is isomorphic between. It's a cyclic group of for gamma 1n, we see that it has to be less information. So right now, our original thing was just elliptic curves. This thing is elliptic curves with a subgroup. And since this is contained in this, it has to be an elliptic curve with less information than an entire group. So what it is just a point of order q. So it's a point on your elliptic curve such that its nth power is the identity, or it's one of the points in this entire group. Is that okay? And the third one is the most difficult one, and I will just say very little about it. It's the isomorphism classes of elliptic curve with a pair of points PQ. So PQ are both points in E tau cross E tau, such that PQ are points of order n, with an additional thing that, so the group of order n has a pairing on it called, so the group of order n on an elliptic curve has a pairing on it called the Weyl pairing. So I will not get in the definition of that, but the property is that that if you apply the Weyl pairing, let me just call it W, to these 2 points, you get a root of unity e to the 2 pi I over n. So these are the 3 different modular interpretations for these curves. Again, this is the easiest one to work with, but this gives you more example and they're necessary. Modular forms, that's the big thing. So let's make a definition. So a modular form of, so it has this invariant associated to it, a modular form of weight k for any of these groups, gamma 0, 1, or something with target n. Is a holomorphic function. Such that so this is the main. Somehow somebody realized that this is the right kind of invariance to look at, such that f of gamma tau is not completely invariant, but rather c tau plus d to the power k, this is the weight, f tau for all gamma in whatever group you're looking at. So this is just this little thing that makes all the difference, that it has to be invariant in this way and not completely invariant. And let me add one more technical thing so one technical thing is that limit as tau goes to I infinity of f tau is bounded. So one main thing, so let's fix, just for the sake of examples, let's fix to the easiest one, gamma 1. And we see that gamma 1 contains this translation matrix 0, 0, 1, 0. Which then implies that if you have a weight k form, then f of tau plus 1 equals f of tau. So it's a function of period 1. And using this, you can take a Fourier expansion and write your function as this thing, a n bigger than or equal to 0, a n f q to the n. Where, so this is the main thing, that you change your variables to e to the 2 pi I tau. And these numbers, so this is where these numbers show up everywhere. And these are basically where all the interesting things happen. So in particular, just as an example, they show up in partition functions in string theory a lot, because in string theory you have the partitions function is supposed to have this S duality and T duality, or S invariance and T invariance, and S is supposed to be the matrix 0, -1, 1, 0. C is 1, 1, 0, 1 exactly. So these two matrices together generate gamma 1. And that's why these coefficients show up as, or these functions show up as partition functions for certain between paired things. And so let me check the time. Okay. So these are modular forms, and the main thing is the following thing. So this is the silliest computation, but this is really at the heart of everything else. So if you look at a function f tau d tau, this is a holomorphic one form on H. And if you compute the following thing, that this differential d gamma tau for gamma in gamma 1 or any one of these things, this transforms simply as c tau plus d raised to power minus 2 d tau. Which then implies that if f was a weight 2 form, then f gamma tau d gamma tau is precisely f d tau. So this thing becomes invariant once you multiply it with this differential. And this then, so f is weight 2. This is my definition for modular form, m2 1. And this is why you have, well, this thing is invariant, but still it's not a really a holomorphic one form, or not a function on that thing. So I have to make one more definition really quickly. So a modular form is so f, let's say a weight k modular form on gamma 1 is a cusp form if in this expansion A0 of x is equal to 0. So this condition somehow means that the modular form, or the such a modular form will vanish at the cusp that we've added on. And now the result is what I stated before. So Sk on gamma 1, these so this denotes the cusp forms, and it's contained in all the modular forms. And because of this little calculation or invariance, we get that S2k, so the even weight ones are H0 x1 times k. There's a deeper reason for this that was given by Deline in trying to attach modus to these things, but I think I'll skip that for now. So should I give some examples of modular forms of these functions? So I just gave them very quickly for gamma 1, and these are the things that people might have seen. So there are these things called Eisenstein Series. They're defined as follows. So it's a weight k modular, it's a weight 2k modular form. It's a weight k modular form, and it's denoted or defined as follows. So E k tau is simply the sum over mn in Z2 minus, so you skip the 0, 0 thing and you're that is Z2, and it's said it tau plus n raised to power 2k. It's convergent and it satisfies the right transformation property that just comes from a simple calculation. So these are called the Eisenstein series of weight k, And then one of the most famous functions in number theory, at least, and I think also in string theory, is this delta function or the discriminant. So this was first studied by so this is a cusp form of weight 12 on gamma 1. And Eisenstein series are never cusp forms. They're exactly in the complement of cusp forms, actually.
I'm sorry. The ring that you wrote in the box, that includes the cusp forms or excludes
No.
them?
This is only cusp forms. So Sk gamma 1, so Sk, so Mk are all modular forms of weight k, and they contain the cusp forms. And cusp forms are have this interpretation as sections of the line bundle.
The pluricanonical.
Yeah, exactly of pluricanonical thing being k is of weight 2k precisely.
And again, this is orbifold pluricanonical,
Yeah.
or it doesn't matter?
No, orbifold, definitely orbifold. If there are no orbifold points, then at the cusps then. See, the cusp forms, as the name suggests, they have this particular thing that A naught F equals 0 forces them to vanish at cusps. That means so the divisor for them are these cusp points. And that's why they become sections of this thing. So that's the important thing, that cusps actually end up being divisors for these powers of canonical line bundle.
Is there a simple way to say that Mk is global sections of some slightly more positive bundle? We put poles of the cusps.
Yeah, that's a very good question. So this I haven't asked anyone specifically from number theory. I had a little bit of discussion with Hitchin about it, and he said yes. I can't really say why. And there is a comment on Math Overflow which says that yes, it's completely obvious that these things, these things are also sections of a line bundle, except that this special thing that they don't vanish at cusps. So I cannot answer this precisely. The feeling is that yes, they are also sections.
I don't understand the comment. I mean, it's completely obvious that there are sections in line bundles. What's not obvious is that the line bundles will not vary with K.
That line bundle will not?
Maybe the line bundle depends on K. Different
Oh,
line bundles for different Ks, but they're given, in the definition of a modular form.
Yeah, but is the
They're
line
given by factors of automorphy. Factors
Right,
of automorphy
right.
describe line bundles.
Agreed.
There's no question with that.
Agreed. So
Sections
yes.
in line bundles.
The
No,
question
but
is how to modify the
Exactly.
canonical
That's
power.
which line bundle. That's
Yeah.
is it still just the kth power of the canonical line
Yeah, is
bundle?
it the
or
K
something
power of
else?
some line bundle, or is it just some collection of line bundles labeled by K?
Exactly.
what's not.
That's yes.
So I'm guessing that it's a kth power modified by something independent of k.
Probably,
Which is just
yeah.
poles at the cup.
Exactly. Probably tensored with the line bundle whose divisors are zeros of the things which are not in the cusp. I mean, somehow you have to modify it, and that I don't know exactly how. And apparently that would be more useful for the Hitchin. I mean, because Eisenstein series are more basic than cusp forms. And somehow people would like to have the Hitchin base as the entire MK and not just SK. So this line bundle thing really has to be thought of more. Anyways, so I should finish quickly because I have 5 minutes and I didn't get to vector operators. So, I mean, I just want to say the first thing one wants to do is probably do this thing as the first example. I mean, look at the spectral curve of this cusp form and see what the spectral curve looks like and what the arithmetic is. But unfortunately, this does not land in the category of viable of Higgs bundles because the curve that they're defined over is gamma 1, which is not of genus bigger than or equal to 2. It's a genus 0 curve with some orbifold points, so that doesn't work. One has to look for other examples of cosmos. I'll just quickly give in a minute what is the intuition behind Hecke operators, or what they're really doing. And then I already stated their main properties in the beginning, so I don't think I need to recall that. So the idea is very simple, and this is what Hecke came up with. So remember, for every tau, so we're looking at the function f tau, and we want to somehow act on it by some operator. So for every tau, we have this lattice lambda tau, and we can look at so we evaluate it basically at all the things f tau prime plus. So let me maybe write it like this: it's the sum over all tau prime in your H, or in the fundamental domain of your group. So let me just say H of f tau prime, such that the lattice associated with tau prime is contained in the original one, and the index of this thing is precisely equal to P if we're looking at the P at Hecke operator. So let's say this is P action. So that's the intuition behind it, that you somehow take the sum over all lattices or over all points which have index P. There is an explicit formula for this thing as well. If somebody wants to see it, they can ask me after the talk and I can write it down, what it is. Or should I just do it? And the more geometric, so this is what Hecke wrote down, but later on people found out that it's the right way to look at it is through correspondences. So for example, if we were looking at a curve xn, then remember, if we have xpn, that naturally covers this thing, because it's a gamma 1 pn is a normal subgroup of gamma n, so it defines a covering. But it covers it in two different ways, and the second way I will not be able to recall right now. P1, P2, and the action is basically given by pull back, push forward. So this is the more modern way of looking at it through correspondences. So there are so one can naturally say now that if you have a Higgs bundle here, how do you transform it after the correspondence? One way is to, well, you have a Higgs bundle, so you construct its spectral cover. At the spectral cover, it becomes a line bundle, and you pull back the line bundle and push it forward. You pull it back to the spectral curve of this thing. But I did something, just to end this talk, something much more basic. So a correspondence for any variety, let me just give the definition and then I finish, it will take 2 minutes. A correspondence on V, any variety, is a subvariety, or really an algebraic cycle in, and let's say it's what should I call it? Let's say it's X contained in V cross V. So then, from V cross V, you obviously have the, so from V cross V, you have the obvious maps to V and V, and restricted to X, they give you two maps to V and V, and this then gives you a correspondence by pull back and push forward. So for every P, we have to somehow construct a subvariety in the product of Hitchin system. And the way to do that is actually really simple. So we have, so the base of the Hitchin system is S4n in this case, and we have a linear operator, EP, mapping this to this. So we can look at the graph of TP, which I call gamma P, and this is just the pair P cross TPF in S4n cross S4n. So we have basically this double thing, MH cross MH, with the Hitchin map, which I denote by this, to S4n cross S4n. We have a subvariety in here, gamma P, so we can look at H bar upper star of gamma P. And this is a subvariety contained in MH cross MH, and its dimension is, so the dimension of this set is 3G minus 3. The relative dimension of this map is 3G minus 3. So it's a total, I mean, and you're doing it on, so the relative dimension of this map is 6G minus 6 because it's on the double of this thing. So the dimension of this thing is 9G minus 9. So it does give you a correspondence because simply by pullback of this map, you do get a subvariety of dimension 9G minus 9. But it's not a nice correspondence in the sense that it's not homogeneous. So homogeneous correspondence is a subvariety which is exactly half the dimension of the product, or a subvariety whose dimension is exactly equal to the dimension of one of these things. So to construct a homogeneous correspondence,
What do you mean by homogeneous?
yeah.
Homogeneous with respect to what?
So a correspondence was a subvariety in V cross V. A correspondence is homogeneous if the dimension of this subvariety is equal to the dimension of V.
That's just the definition.
Yeah. But the nice property of a homogeneous correspondence is that if you pull back an algebraic variety, so if X were a homogeneous correspondence, pull back of some subvariety here of dimension n, and then the push forward will give you a subvariety of dimension n. But if it's not homogeneous, these dimensions will change. So that's why it's called homogeneous, I guess, because it takes the same dimension to same dimension. So the point is somehow to construct a 6G minus 6 variety out of this 9G minus 9. So the way to do that is, let's just, for the sake of, let's call this gamma P tilde. So if we simply intersect it with some 9G minus 9 variety in here, then the intersection will be, so the dimension of the intersection will be equal to 6G minus 6. So there's a nice 9G minus 9 variety here, and that's the total. So Q equals the total space of the fiber bundle over S4n cross S4n, where the fiber, so let me just write it as PF prime right now, and the fiber PF is defined as and if we take F comma F prime in here, then the fiber upstairs is a 3G minus 3 dimensional variety, which I just write down as PF cross PF prime over MB. So this is so what we do know is that if we have two spectral curves or two fibers of the Hitchin system, let's say F, there's this abelianization map, or there's a dominant map of this abelian variety of the moduli space of bundles of certain degree. So it wouldn't be degree 0 because we're looking at degree 0 line bundles. When you push them forward, they become a line bundle of high degree. And there's also, I mean, you can do this for the other prim variety as well. So when you have this, you can construct the fiber product F prime over MB, and its dimension is equal to 3G minus 3 exactly. Because 3G minus 3, 3G minus 3, 3G minus 3, so if you just do the formula, you get 3G minus 3. So the fiber over such a thing is of 3G minus 3. This thing is 6G minus 6. So Q is of 9G minus 9 dimension. And their intersection then gives a 6G minus 6 dimensional thing. And this is, so I would call this, so I define TP, the correspondence, to be the intersection of gamma P intersect Q. This is what will give, so this subvariety lifts the action of Hecke correspondences on the base of the Hitchin system. And there's one very interesting thing to do here now, and this is where all the number theory will kick in, because we're after all we're after some kind of numbers. So now we have the 6G minus, so we have a subvariety of half a dimension. If we also have another subvariety of half the dimension and we intersect them, they will intersect in 0-dimensional cycles. So, and that will give you the number of intersection points. And the obvious half-dimensional cycle is the diagonal in MH cross MH. So the diagonal contained in MH cross MH. And so we can do delta intersect this cycle, T tilde P, and let's define it to be some number, let's say, I'm out of letters, MP. So for each prime number, so I want to say the cardinality of this intersection equals MP, which is an integer. And so the following conjecture is inspired by Don's thesis about intersection numbers and they generating modular forms. So remember, like this form or this expansion of modular forms that we have. So we can construct a function, let's call it f tau, to be equal to the sum. Actually, let me write it as a sum over all n bigger than or equal to 1, where we sum over intersections of t tilde m q to the n. So this is a modular form itself. I cannot guess the weight and the level of it right now, but nonetheless we have these numbers, and if there's any justice, this should be a modular form itself. So there's a lot more to say, but thank you so much. I think I've already taken enough time. Any questions?
Tn was defined for all ends, or you had?
Yeah,
ends that were
thank you so much for the good point. So I was just saying Hecke operators for P where P is a prime. Hecke operators are defined for all integers. I mean, they're easier to define for P, for a prime number. And then you take, for any integer, you take the decomposition of that integer in its prime components.
I thought you had to assume that the prime was relatively prime to the conductor or something.
Yeah, so you will have to skip those primes which divide n.
Exactly. Yeah, so what do you do in the sum when you get one of the primes that you're excluding?
They are, okay, so the Hecke operators are also, The definition is different for primes that divide n, but there is a definition. I'll tell you exactly what happens. It's similar to having bad reduction at P. So really what happens is that, this is the Eichler-Shimura relation, which says that the Hecke operator is actually equal to the Frobenius at P. And the modular curve has bad reduction exactly at those primes which divide n. So there is a definition for bad reduction and things like that, but it's just more complicated, so I wanted to avoid that. So for p's that do divide n, there is a definition, but it's more involved.
But geometrically, you're still going from cyclic p subgroups to other cyclic p subgroups of the same curve?
Yes. Yes. So again, thanks for pointing that out. I never gave the definition. That is the right way to look at Hecke operators. They take elliptic curves with some torsion data, say the order p thing, to elliptic curves with torsion data, the original p, the original c plus p, if it's a p at Hecke operator. So yeah, exactly. That is what happens. And just as a comment, this modular form will be special because the coefficients of modular forms, those a and s, in general are not integer values. They're always algebraic integers, but not rational integers. In fact, that's the Taniyama-Weil, Shimura, Wiles, blah, blah, blah. That's the elliptic curve and the modularity thing that weight 2, now I can write down the modularity theorem that a weight 2 modular form whose coefficients are integers, they are actually L functions of elliptic curves with conductor n, and the conductor being the level of the modular.
Other questions? Thank you very much.
I'm sorry, I really went over time.